just move on to Professor Breyer at the LUT University in Finland. He will be talking about the role of hydrogen as an energy carrier for energy industry systems within the PtX economy. Professor Breyer.
Yeah, it's a great pleasure to have the opportunity to talk. Hopefully it works. Now I see a freeze.
It's frozen. I can see your mouse, but you're coming through.
Maybe yes, now it works.
Yes.
Okay, perfect. Great. Let's get started. Yeah.
Before you start, how do you pronounce the L in the LUT, please, of the university?
Lappeenranta.
I'm glad I didn't have to say. Okay, thank you.
Anyway, okay, yeah, it's my pleasure to give an overview from a systemic perspective on the role of hydrogen as an energy carrier in overall energy industry systems and embedded in the PtX economy. Why all those perspectives? I will show you through the slides. What we had not yet heard that much today in the presentations is the overall framing. I think I have not to lose too much words on climate change, which drastically push the transition. What you see in this diagram top left is what in 1 single hour on annual average Iceland is losing ice. And this is Greenland. This is only Greenland. So we have pressure all around due to climate change. What you see in the next diagram is the resources. The orange, circles representing on the left side of that diagram represent the primary energy demand we have in the world. And then we have the resources. The resources tell us if we tap the sun, we have no energy resource challenge at all. However, wind and other renewables are also available. Maybe, and this is something we have not yet heard so much today as well, is efficiency in the system. And the efficiency means whenever we have the opportunity to go for a direct electrification, we in the end will do that. And the reason is not only efficiency, it's simply low cost. We see that in electricity generation, so thermal processes are incredibly inefficient, finally due to a second law of thermodynamics. If we have lower temperature heat, we can do quite a lot with heat pumps. And in the transport sector, sorry to say from a hydrogen perspective, but on road transportation, hydrogen will have most likely no great future. And the reason is simply it's not efficient enough for direct electric solutions with batteries. What finally pushes the entire transition is rapidly declining costs. So we have huge cost decline in PV. We had it earlier in wind. Currently, we see brutal cost decline in batteries. And all this is pushed by increasing volume. So from that point of view, we are right on track. And this is a diagram from Bloomberg New Energy Finance, and it shows the transition in new power capacity installations annually normalized to all installations globally of the last 15 years. And you see starting from low shares, solar, not that low shares of wind. After 15 years, we have a dominance of solar and wind. A few fossils are still there, a little bit coal, a little bit gas. Nuclear practically disappeared. It's not affordable. Some bioenergy. However, this is the year to 22. From 22 to 23, global installations in PV increased by a further 70% annually, and in 24 by a further 24%. So nowadays, global newly added capacity is dominated by PV. Last year, according to numbers from IRENA, we had more than 90% of all global installed capacity was renewable. So from that point of view, we are not bad on track when it comes to new installation in the power sector. And that, of course, is very important because somewhere we need the energy to get all the hydrogen. This is an overview on studies on highly renewables, typically 100% renewable global studies. You see wind on the y-axis, PV on the x-axis. And the closer the dots are to this 80, 90, 100% line, the more it means that together wind and solar go for full supply of energy. The green dots tell the story from electricity. The blue dots are the even more important one for our today's consideration because it's the total primary energy demand. And there are two. The one is the team of Mark Jacobson in Stanford. The other is my team that can show that with wind and solar together, one can reach more than 80% of all total primary energy supply. And that obviously includes a lot of power to X, in particular power to hydrogen and hydrogen to X. Interestingly, the Stanford team did it more with wind, and in my team, we find a higher share of solar. It's maybe due to some different assumptions, modeling backgrounds, and others. But in the end, we can do that, and we find different pathways. In the following, I show the one or the other result based on the LUT energy system transition model. With that model, one can go for any kind of energy scenarios, whether it's more fossil, more nuclear, more renewable, it doesn't matter too much. However, on what it was really optimized is all kinds of power to X routes. They can be power to heat, which was, I think, a kind of a classical one, power to fuels, which typically start with hydrogen, but typically not that many are really interested in hydrogen. What we're really interested in is ammonia, methanol, and kerosene jet fuel. So then there's typically one process step further. Whether it's a fuel or a chemical depends on the perspective. Then, of course, materials, for sure, we will need direct hydrogen as a kind of feedstock for steel making. Power to X, however, can be also fresh water, which I think on seawater desalination. It can be CO2 when we talk on carbon dioxide removal. With some special applications, it can even lead via desalination to forests. And on my very, very last slide, I will show power to food, which, by the way, also starts with hydrogen, but in the end, the output are proteins. So this is the basis, and we nowadays talk on energy industry CDR systems. So it's more, that's all from an energy perspective, but it's more than the classical inner core of an energy system. Starting here, framing some background, is a study that could showed a few years ago that there is a cost-neutral transition to a highly renewable energy system possible, and this covered the full energy system, so power, heat, transport, in particular with marine and aviation, so there were more complicated parts. It requires massive investments from a CapEx point of view. However, on an annualized system cost point of view, it's more or less cost neutral. And this is very important given the needs for hydrogen-based fuels, because they cost a bit more. However, we can reduce some cost when it comes to direct electrification, whether it's on the road, whether it's in the heat segment and others. And of course, it avoids harmful emissions, whether it's CO2 or very harmful air pollution. Was also not yet that much mentioned today. So several million people per year die due to air pollution from burning fossil fuels, so that we can do better. This is now a study on the case of Europe. It was modeled Europe in 20 regions, full hourly resolution, different scenarios, full sector coupling from energy and industry. Industry described on a process level with energy-intensive industry, in particular cement, steel, chemicals, pulp and paper, and aluminium. And the target of this scenario was to show, because we know the carbon budget for 1.5 degrees is practically fully consumed. It was even consumed 2-3 years ago. So we are already in a deficit. All the rest is a kind of a self-betray, or we calculate with 50% chances to reach the target. No one of us would even enter a plane or a train with 90% chance to reach the target safely. So it's a bit insane what we do. However, anyway, the way was it should be of zero emission by 2040, because we are in delay, but it will be more ambitious than 2050. Is it doable? What does it mean? And levelized cost of final energy, so it's not only electricity, it's the full energy system, including feedstock, would remain a slight increase of cost, but still much, much lower than we saw during the energy crisis of the last few years. So from that point of view, should be well on the good side. And of course, we have a lot of benefits when it comes to environmental impact, air pollution, biodiversity issues, and others. So taking the broader perspective should be fine. When we see to the phase out of CO2 emissions, it's well possible to reach it in 2040. The remaining one is the limestone CO2 part of cement. So that will be tackled with carbon capture and sequestration. The consequence is massively increasing electricity demand. And now starting the story on hydrogen, from now onwards I will talk largely on hydrogen and e-fuels and chemicals, is the diagram on the bottom left. And we missed in the first round the meaning, but we found it in other world regions later on as well. From all the fuels and chemicals we use today, if we have a fully renewable, as much electrified system as possible, 40% of this fuels and chemicals demand remain. So that we don't get off the table. This is due to chemical industry, steel demand, international marine and aviation transportation. And from that, the lion's share has to do with hydrogen. So we can have some sustainable bioenergy. So no energy crops are included in the scenario. It's only sustainable byproduct of bioenergy. But then we have direct hydrogen. Then we have kerosene jet fuels, or here called Fischer-Tropsch fuels. And then methanol and ammonia, both used for the marine transportation, but in particular chemical industry. And that we cannot avoid. This is the energy flow of the energy system today. I will not go into details, only tell you this is silo thinking. So the sectors are separated. Now let me explain it in a bit more detailed what a sector coupled system means and what is the role of hydrogen in that. On the right hand side, you see the demand sectors, so power, industry, heat, transport from an energy industry system. On the left-hand side, you see the inputs. It's largely renewable electricity. For the case of Europe, it's roughly half wind and solar, with some support of hydrogen, hydropower, maybe some wave power and some others, but it's largely wind and solar. Environmental heat, so this is what comes from heat pumps, and then some sustainable biomass. The blue flow here and all the flows you see, I would call the metabolism of the energy system. As said, it's as much brushed to direct electricity use, but still it's a cost optimized scenario for Europe in 20 regions, hourly resolution, and in 5-year time step. That's this the picture for 2050. And the blue stream here in the center, this is hydrogen. This is very, very large. So it's the second most important energy carrier, no doubt on that. Most important is electricity. Second is hydrogen. But, and this is something we should discuss and consider more in all our considerations, no one is really interested in the hydrogen, or at least not that many. What most are interested in is ammonia, methanol, and jet fuel. And this brings a kind of a different systemic dynamics on that. This is just briefly showing how it was done in an hourly resolution, so which is with real weather data. Most important is this orange part here on the top. So you see the best resource week of the year is in May, the worst in November due to Dunkelflaute, it's very often called. When solar is not perfect, we have fog, no perfect winds, but still the entire system is stable, no doubt on that. We should be not that much concerned. But a very important fraction is this orange one here. And if you look to the legend, it's called power to fuels. And this is when electrolyzers running to produce the hydrogen, which is then in the sequence step converted in synthesis units to ammonia, methanol, and jet fuel. If we have excellent resources, wind and solar, then this is produced, and then it goes in underground buffer storage. If we have no excellent resources, then just this component goes very, very low. So this is one of the central balancing mechanism in such a system. Due to the running time, I will not go too much into details how an underground hydrogen storage may look like. What you see here is on the x-axis, the 365 days of a year and the 24 hours of a day. And we found so far 4 archetypes of an underground hydrogen storage. It can be fully seasonal. So this was a case by accident in Hawaii. We've not yet fully understood why Hawaii, but here you can find a seasonal storage. So it's charging through months of the year, then discharging in some phases where it's lack of resources, then it's empty and then it's recharged. So this is a standard seasonal behavior. Then classical buffer storage, this is top right, that we found on the case of Finland. So whenever there is wind and solar available, wind in the winter half year, solar in the summer half year. So as of now in May in Finland, we can have 18 hours of sunshine from in the morning of, let's say, 5 o'clock, 6 o'clock to late evening, 10 o'clock, and this is for several months. So there is excellent solar resource in the summer, but it's wind in the winter half year. Whenever this is available, it goes into the buffer storage and then it goes out with baseload supply, so classical buffer storage. What we found by accident for the Caribbean in Puerto Rico is a kind of a daily behavior, similar what we find with batteries, but still there is some wind power still. You see these stripes. This is whenever wind is available. And what I personally like most is Iberia. So Spain is top left. It has the daily characteristic. It has the seasonal characteristic. And still you see the wind. So there is a kind of a superposition of all those different factors. Now coming to the overall demand of fuels and chemicals, surprisingly, that might be rather stable, while we see some energy service demands growing, in particular chemicals, in particular international marine and aviation fuels, assuming people are still traveling and goods are still transported. However, a massive reduction in liquid hydrocarbon fuels, in particular road transportation. No one needs that anymore when we switch to battery electric vehicles. But all in all, so we have declining factors, we have increasing factors, but all in all, the demand might be rather stable. Now is the question, what are the main fuels? And it took us some years, some time to go through all the fuels. Hydrogen, ammonia, methanol, and Fischer-Tropsch liquids. To sum up, all of them can be produced. In the, let's say, next 10, 15 years, the wind-rich regions in the world have really good, how to say, starting points to get it on low cost. Let's say from 10 years onwards, 15 years onwards, the excellent solar sites on planet have just the best competitive edge. But it's a very important but, always given low cost of capital. So the best sunshine in a challenging region in the world is of no help. And a good example is Somalia and Yemen. We would find for good cost of capital one of the best sites in the world at all in Somalia and Yemen, but with the cost of capital in this very, very risky region, it will not work at all. So the combination is excellent resource sites and super stable conditions, excellent governance, low risk, excellent, how to say, doing of business environment to have low cost of capital. That is the booster for all those fuels. Then we looked into the infrastructure, and there I saw some comments today I would question or partly disagree. So transporting hydrogen, from my point of view, over long distances is, sorry to say that clearly nonsense. And the reason is we can simply not afford this extremely high cost, and it does not make that much sense. And the reason is we typically need ammonia, methanol, jet fuel. However, if we do the transport with ammonia or methanol or oil products in general, jet fuel, others, we have, first of all, an infrastructure today. We have all the transportation facilities today, whether pipeline or ships. And this is the most important, compared to new infrastructure with hydrogen, maybe there is some window of opportunity for using the existing gas infrastructure, natural gas infrastructure for hydrogen. But for new infrastructure, let's have a distance of 2,000 kilometers. Why we took 2,000 kilometers? This will be the distance from Finland to Germany. Germany is a main importer, but it could be Belgium and Netherlands as well. But Finland could export wind-based. But if you then compare the transport cost, you find a factor 9 to 15 in between with the cost of hydrogen transport versus ammonia or methanol. So to cut a long story short, we will transport the products we need, but not the hydrogen. It's simply too expensive if you take the cost. And we're not talking on a few euros per megawatt hour. We talk on the order of 20. So that's really, really expensive. You might be interested in this paper. It's the first link in the source below, because this, from my point of view, or to our knowledge, is the paper with the highest hydrogen demand ever published. And here you can find 60,000 terawatt hours of hydrogen by 2050, largely driven by demand in the energy system. Energy system is largely the transport system, so marine and in particular aviation, then steel making, and then chemical feedstock. However, this is then typically, how to say, hydrogen-based products. As you can see here, there's still some hydrogen. Methane, I have increasingly doubts on that. Maybe that's more than consumed by others. But then the Fischer-Tropsch liquids, ammonia and methanol. So there will be huge demand for all of that. Coming to my very last slide, and maybe this is a kind of a view on the far horizon. We always talk on fuels and chemicals, but maybe soon we talk on food. And this is a study we just recently published in Nature Communications earlier this year. is about the opportunity to start with renewable electricity, convert it to hydrogen, take ammonia, of course, again, hydrogen-based, take CO2, best from the air with direct air capture. Then we need very clever bacteria in a biotechnological process, and the output is protein. How to say, contribute to one of the major challenges in the decades to come, how to organize a stable, sustainable food supply for 10 billion people, because arable land globally is shrinking. That's really a problem, a much larger problem than the energy system. That's it. So from the summary, electrification is low cost and highly efficient. So whenever this is possible, we will go for that. PV develops beyond any historic experience, but still it's complemented by wind power and by other renewables, so no doubt on that. Flexibility is the key for a low-cost energy system, and this is supply complementarity, wind, solar. I mentioned the case of Finland, but you find it everywhere in the world. Grids, demand response, curtailment, storage, all this contributes to that. Hydrogen hype, I would call, blocks a bit the view on the real solutions. First of all, it's direct electrification, and then it's hydrogen to X for fuels, for chemicals, in particular ammonia, methanol, jet fuel. The transport of hydrogen is finally too costly over long distances. A few hundreds of kilometers, I would not argue against. So 500 kilometers, something like that, we will have everywhere in the world. No doubt on that, but long distance. And the reason is hydrogen to X products have just a fraction of the cost. Ranking of the energy carriers, most important is electricity, then comes hydrogen, and then, by the way, methanol. The PtX economy, I would say, is the core characteristic of the energy system, and what we typically call as a hydrogen economy is a subset of that. Then many thanks to all of your attention and to my team, because without this team, such beautiful insights would not be possible. I'm very happy to take all your questions. If you have not time here, then of course in the chat.